Right, guys, welcome back. Please could you comment your names so I know who's there. So post some comments now. Cool. All right, so we got Roddy. Just logging back in. Right, Roddy and Fifi and Sophie, Becca, Callum. Cool. Be right back. Alex. Cool. Anybody else out there? We need Caleb, Charlie, Joan, George, and Leo. If you guys are there. Cool. Hey, George. All right. We'll get started. So, yeah. So for the last bit of this term, we are going to be looking at the last kind of bit of complex numbers for now. And the topic we're going to be looking at is a topic called Argand diagrams. Cool. Here we go. All right. So these are just Joan's here. Hey, Joan. Cool. All right, so these are a diagram made famous by a guy called Jean-Robert Argand, and he was pretty good at maths. He also is the guy behind this line, this symbol for vectors, and he was the guy behind the modular signs for the magnitude of a vector. So he lots of signs and diagrams. So he got these Argand diagram things named after him. They're a really good way of showing complex numbers on a graph, which lets us be able to do kind of vector calculus. So you can tell he was into his vectors. So yeah, Argand diagrams are useful. They let you kind of treat complex numbers as vectors, and kind of show them as well, so we get visual representation of vector of complex numbers. So I'm just going to rewrite this. So as you can see, the idea is we're going to use the x-axis as the real axis and the y-axis as the complex axis, or the imaginary axis if you like. So we're going to write IM for imaginary and RE for real. Now of course, it's not always going to be positive. We could have negatives in either as well. So IM is for all our complex bits, or our imaginary bits, because we're talking about complex numbers, and RE is for the real bits. Hey Leo, I'll just swap you in. Alright, so for example, if we had a complex number z equals x plus I y, we can now show that on an Argand diagram by doing the following. So we can say, well, this is x in the real direction, and it's y in the imaginary direction. So that would be my complex number. And later on, we're going to see there's a few other ways of saying where this point is using what's on our diagram. All right, everybody with me so far? So this is an Argand diagram. It's a way of showing a complex number on a set of axes. We use y for the imaginary axes and x for the real part of our complex number. Hey Caleb, have you, if you have missed the beginning, if you want to rewind it, I should be able to catch up later. Anybody heard from Charlie today? He's the only one missing. Okie dokie. So, for example, if I get rid of all that, GG. Sketch Z equals 3 minus 2i 1 Argand diagram. So 3 take 2i, it's going to be 3 in the real, so there's 3, and minus 2 in the imaginary, so there's 2i there. So that would be my location, and we can draw an arrow to that as well. The arrow is something we're going to talk about later. Also, the angle we make, we're going to talk about later. Possibly today, if not today, certainly tomorrow as well. Right. So I would like you guys to try and draw these three. The first one can be a little bit clearer there. I'd like you guys to try and draw those three on the same Argand diagram. And then I'd like you to have to think about what you notice about 2 and 3. So where I want you to do this, I'm just going to give you guys a call on Microsoft Teams. I'd like you guys to draw those, take a photo of it, and upload it into the chat box on Teams just so I can see that this is making sense to everybody. So I'll set that up now. I won't say anything on Teams because otherwise we're going to have like 2 different audio streams with a delay in the middle. So calling you guys now. So if you guys can mute yourselves because I'm doing this through the speakers, so you'll hear a load of feedback if you don't. I think that's everybody. Leo, you're not on my list. I will try and add you anyway. Cool, Leo's been added. If you guys could all mute yourselves, that'd be great. Roddy, you're also not on my list. Is everybody?
That's such a good background.
Thank you. Who's that? Is that Joan? Sophie. Cool. Right, so if you guys are all there, that was Joan. Cool. Thank you. Cool. Could you guys try that question? I'll give you 5 minutes to do it, and then can you take a photo and upload your photo in the chat box on why am I doing this? On Microsoft Teams so I can see how you go. Thank you. All right, I'll be back in 5. Give that a go. See you in a sec. 5 minutes starts. Callum, log on to Teams, answer the video call, then you've got 5 minutes to try these questions and take a picture of your answers and post them to me on Teams. Cool. Yeah, 5 minutes started just now. Cool. Right, I'm just having a look through your Argand diagrams now. If I can get in the right one. Cool. Cool. So, Fifi was first by quite a long while, so well done, Fifi. So you got -4, 1. Yeah, I mean, you could have done some labels though, is all I would say. And yeah, apart from lack of labels, like it, good sketch. Brother, yours are all on different things. That's all right. Yeah, yep, solid work there. Who's that one? George, yeah, nice. You don't have to label the whole axis with a sketch, but that's good. Yeah, I like it. Sophie, yeah, great, nice. Rebecca, very good. Yep, label your axes, but good. Vivi, I thought yours was pretty good. I think George's was the ugliest. Who's was that? That's very good. Callum, very nice sketch there. Alex, yeah, very good. Is that everybody? Joanne, yours is the messiest, I reckon, but it's sketch, it's functional. Charlie, yeah, pretty good. This is taking ages, isn't it? Cool. Use the key. You don't have to use the ruler, it's fine. All right, Leo, are you there? If you're there, can I have some pictures from you as well, please? All right, so I'll draw these, and could you guys have a quick think? What do you notice about Allen Key has 2 L's and an E in it? What do you notice about the 2 and 3 sketches? So while I do this, have a quick think. I don't mind where you comment. I know there's 2 chats now. I'm going to just make a bit of space so I can see both sets of chat. Cool. Right, so I'm going to draw these quickly. Can you guys, what do you notice about 2 and 3? Cool. It did say on the same Argand diagram, so if you did do them separately, you didn't read the question very well. But there we go. Okay, so right. So nice set of axes. I am RE. So you've got -4, 1. There's one there. 2 and then 3 I. So 2 is there. 3 I can be there. You don't need to put the lines in. I'm just doing it because it's going to match up with what we do on tomorrow's lecture. So I'm doing it because I know what's coming, but you don't have to. And then 2 minus 3 I. So that would be... yeah. Okay, so what do you notice about these two? So Callum has said reflection. Yeah, specifically what they're reflected in, though. So I agree, it is a reflection. Reflection in the line. What? They do form the same angle with the x-axis. That's going to be important. So yeah, they form the same angle there. What else, though? And what are these things? What do we call these things? So just to recap what we're doing before half term, what are these two things called together? What line do they reflect in? I'm just going to wait here awkwardly until you guys give me some more answers. They are both complex numbers, yeah, but all three of them are complex numbers. Conjugate pair, yeah. So these are complex conjugates. Okay, and what line do they reflect in? The real axis. Yeah, what is it there? It's the x-axis. So reflect in the line y equals x. So that's interesting. If you've got complex conjugates, they will reflect in that line. They'll be symmetrical about the axis. Could be this way when we're doing it like this, or they could be that way. Yeah. So complex conjugates reflect like that. Is that a glass liter beer tankard? Yeah. It's actually plastic. Yeah. Cool. Yes, complex conjugates. We'll write that down. So on an Argand diagram, the complex conjugate is the reflection sorry, not y, because x, what am I talking about? In the x equals 0 axis, sorry, that was a mistake. Reflection in the x-axis, yeah, sorry, do apologise there. Because y equals x would obviously be that way. Alright, complex conjugate in the reflection is the reflection in the line y equals x. Who's this scrub? Let's block them. Cool. Well spotted though, Fifi, yeah, not line y equals x. Alright, next one. So yeah, we can kind of use vectors to describe this. So you've seen, like, for this last one, it was it 3? No, 2. I can't remember what it was. 2 plus 3i. 2 plus 3i. We can write that kind of in vector form. So in an Argand diagram, you've got the x is real, the y is imaginary. So we can use a vector form of a complex number. Who's this? Who are all these randoms? Roddy, do you want to be a moderator? You can be my moderator in the chat. There you go. That could be a dangerous decision. But yeah. Anyway, so yeah, vectors, if you got z equals x plus iy, we can say that's xy as a vector form on the Argand diagram. So we can take those two components, the x component, the real component, and the y component, the imaginary component, and write them as xy on our as a vector on the Argand diagram. Cool. Right, so I would like you guys to try and sketch these two complex numbers, and then hence use the diagram plus vectors. Can't remember what vectors there. So sketch them both on the same diagram, and then use the diagram, and you can use vectors to try and find z1 plus z2 on the Argand diagram. Cool. If you guys give that a go, and then comment your take a picture of it and comment your workings in the what's it called, the Teams chat, and yeah, I'll give you 5 minutes to work out that one. Cool. Right, 5 minutes starts now. Cool. All right. Yeah, some good answers there. I think everyone's was right apart from Fifi, and you. All you did was you read it wrong and did one take the other instead, and you were right with your answer for that. You did Z1 minus Z2 instead of Z1 plus Z2. Cool. Who was that last one? Sophie. Yeah, nice. Cool. All right. So how I would have done it, I would have just kind of thought about it in terms of vectors from this point. So if I draw both of these on the same diagram, I am RE. We've got 1 is 4 plus 1, so 4 plus I, which is going to be there. So there's Z1. Z2 is 3 plus 3i, so 3i. It's going to be like that. If I add those together, I can just kind of like put Z2 on Z1, draw the overall vector, and then find out what that is. So if I take Z2 and kind of place it, there's Z2. So Z1 plus Z2 is this yellow vector, which is going to be just adding them both together. So we got Z1 plus Z2 is going to be 7 plus 4i. We could write it as 7, 4 if you want it as well. Cool. Everybody okay with that? Seeing what the Caleb. Okay, Caleb. No worries. Yeah, if you want to do something for work, you can. I don't mind. That's all right. I trust you. Cool. All right. Yeah. Alternatively, I guess you could just draw it going through the middle. You can kind of think about they're both gonna. You could think about resolving them. So you back from mechanics, you could think resolve this one this way, and the combined total is this amount. That's the thing when you get into vectors and complex numbers and resolving. It's all kind of the same thing. Is the yellow angle a bisector of the angle between the two vectors? Would it bisect it perfectly? Oh, that's interesting. You tell me if you want to work it out, Roddy. It's going to be tan. What would it be? Tan of the y bit over the x bit. Work it out. I think it would it be. I was trying to think this through geometrically. If you move that one up, would it still bisect? Don't know. See if you can prove it. That's a really interesting question. Oh, cool. It's working now. Good. Let's just check Caleb's. Yeah, good. Just don't forget to label your axes, Caleb. Cool. All right. All right. I've got 5 here for you to do. Part 1 should be pretty easy. I'm going to cross half these out because you guys are finding very simple. So 4 to do there, and let's cross out those 2 as well. I think that would be pretty dull otherwise. So there you go, guys. It's going to be what 4, 5, 6 questions to do. Is it parallelogram? Let me just have a look at it. Yeah, okay, yeah, no, I think you're right, yeah. Yeah, it would be a parallelogram. Yeah, okay, I reckon there is a rule we can say then. That's only if they're added. I don't know if they're subtracted. But anyway, so could you guys try these ones? 6 questions. Give it a go. Post a picture when you've done all 6. I'll give you guys 10 minutes for that. And if you're all done by then, brilliant. But yeah, 10 minutes starting from cool. Yeah, pretty good from everyone as I saw. There's a couple of new ones here. Yeah, looking good. Let's quickly go through these then. So first bit, let's put them all on one diagram, save a bit of time. So 7 plus 2i, 7, 2i. So that's there. Minus 2 plus 5i. That'll be there. 3i will be just that. And minus 4, obviously. Let's make it grey. Minus 4 would just be sat on that axis there. Cool. Right, next bit. Show Z1, Z2, and Z1 plus Z2 on the Argand diagram. So we've got 11 plus 2i. Two plus 4i. And adding those together will be over there, up there. So that one there. I guess we should find it too. So that's going to be 13 plus 6i. And the last one, minus 6 minus 5i, so that's minus 6. Minus 5i is going to be there. Z2 is going to be minus 4 plus 4i, so minus 4 plus 4i. And we're doing what? Z1 take Z2. So you think of that in terms of vectors, is going to be Z1, which brings us down here, minus Z2 is going to take us back in that direction, which is going to be here. So Z1 takes Z2 overall will be this vector here, and we can work that out, and that's going to be minus, what's that going to be, minus 6 minus 4, so minus 2. So I've not drawn that very well. We'll correct it in a minute. Minus 2 and then minus 9. So really, it should probably look a bit more like that. But my drawing was on scale anyway. So we could say minus 2, minus 9 in terms of complex vector. Yeah, cool. Which I think you guys all pretty much got there. So well done, everybody. Okay, what's next? 2 more. Okay, well, we're going through this very quickly. Let's try 7 and 8, and then if you get those done quickly, there is a challenge question at the bottom. Let's give you guys 12 minutes. 12 minutes to do. The first 7 should be easy. 8's a bit trickier. Challenge should be alright, but yeah, I'll give you guys a little bit longer. So 12 minutes. Again, please post up photos when you've done it, just so I can check as you go. Right, how are you guys getting on? I don't think anyone's done the challenge yet. I'll give you guys another 5 minutes because we got some time, and I'd like to see if you guys can do this. There's a hint. Check the hint. The hint makes it pretty easy. So 5 more minutes. Comment when you're done. Right, let's go through these then. Fifi, that's okay. Yeah. And George, yeah, fine. Alright, so working through the first bit, find P and Q. So if I'm going to do this all in vector form because it's a bit easier then. So Z1 plus Z2 is Z3. So minus 8, 5 equals PQ plus 9 minus 5. So therefore, P equals minus 17. And Q is 10. Yeah, just checking that in my head. Yeah, that's right. Cool. Show these on the Argand diagram. Okay. So Z1 minus 17, 10i. Z2 is 9 minus 5. Minus 5 right there. And minus 8, 5. So minus 8. 5i. It's probably not on the same line. I don't think it's far off though. Cool. So those ones. Next bit. Question 8 here. So trying to solve this quadratic. So you can use quadratic formula. I'm going to complete square. So z minus 3 squared minus 9 plus 10 equals 0. So z minus 3 is I. So z plus minus I. Z equals 3 plus or minus I. Cool. Show on the Argand diagram the points representing the complex numbers. Well, because they're complex conjugates, they are going to be there's 3. We can have I there, minus I there, symmetrical about the x-axis, like we saw before. All right, challenge question. Find all the solutions to this. Okay, so they've told us the 6 roots in total, and they've told us we can complete the square. So the way they've done that is they said z to the 6, take 1, is 0. Those are both squared numbers. They don't look like it, but they are square numbers. So we can do difference of squares there to get z cubed minus 1, z cubed plus 1. Equals 0, so we get z cubed equals 1, and z cubed is equal to minus 1. So z cubed equals 1. Well, 1 is a root, and also yeah, just 1 is a root there. For z cubed is minus 1. For that one, we're going to get z equals minus 1 in there as well. Is that right? Yes. But we also get complex numbers as well. So solving that one. How have you guys gone about this one then? So Z. Oh, yeah, okay, so take those two both out as factors. So we got z minus 1, z plus 1. Should you guys use long division on this, or? I can't see how else we can do that other than long division. So if we do minus 1 into there, that's going to give me z to the 4 on top. Plus minus z squared. So that's going to be, oops, have I done a minus 1 there? No, that's fine. I'm skipping ahead a bit though. So subtract those, and we get z to the 4 minus 1. So z squared minus 1 into that is going to go plus z squared. Minus z squared. So that's going to give us z squared take 1, which gives us a plus 1 on top there. Yeah, I think. So we get this quartic. So that's going to factorize as z squared what am I doing? Surely those will both be plus 1 though. No, that's not going to factorize, is it? Okay, so z squared equals x. We're going to basically get x squared plus x plus 1 equals 0. X plus 1 squared minus 1 plus 1 equals 0. So z squared plus 1 squared equals 0. It's going to get z is plus minus 1 again. What am I missing here, guys? I did this yesterday and I cannot remember what I did differently. Yeah, Roddy, how did you get your plus minus root 3/4 I on this? Z cubed minus 1 z cubed plus 1. We're saying George z squared plus z plus 1 source or one of the other. solutions. Where do you get that from? Is that what I just had and got rid of? Yeah, that is. I don't see how that does though, because we surely would get z plus 1 minus 1 plus 1 equals 0. The 1 and the 1 are going to cancel. We get z plus 1 equals 0. Z equals. I'm sorry, yeah, z equals minus 1 and z was. So we just get I and minus I. What did I have? Let me rewind. I had z to the 4 plus z squared plus 1 is 0. And then we could say, I don't know, y equals z squared to get y squared plus y plus 1 equals 0. So y plus 1 take 1 plus 1 equals 0. So y is minus 1, so therefore z squared is minus 1, so z is plus minus I. So that gets me 4 solutions. 1 minus 1 I minus I. Is that? What else am I missing though? So, yeah, surely that only solves for plus and minus I. But there's 6 distinct roots in total. Where are these other 2 roots coming from? Anyone tell me? This is surely a challenge question. Oh, are we dividing it? Yeah, okay. Okay, I see. Oh, this is a pain in the neck. And then write it as z minus I, z plus I suppose. And expand that and use long division again. Z squared plus IZ minus I squared, which is going to be minus 1, so plus 1, so Z squared. Plus 1, okay. Yeah, I see. So then back to long division again with z squared, or z to the 6 minus 1 plus 1, z to the 4, z to the 6 plus z to the 4. So we get minus z to the 4 minus 1 minus z squared minus z to the 4 minus z squared, z squared minus 1. Is that right? No, do I do? No, that's right. Let me just check this through. Okay, so z squared into that is going to go You're not going to get a remainder now? Oh, sorry guys, I should have done this before. Z squares into that go plus 1. Let's do that again. Alright, z to the 4, z to the 6, plus z to the 4, subtract, minus z to the 4, minus 1, minus z squared, minus z to the 4, minus z squared, subtract those, z squared, minus 1. What am I doing wrong? Should it be minus? Should it be plus 1? Anybody spot my mistake in here? Otherwise I get remainder, which I shouldn't because those should definitely be factors. That'd be plus 1, z squared, yeah, z 1 times 1. And that doesn't work. 1 minus 1 is going to be minus 2. Anybody got a proof for this, why it's working? I can see, George, why, yeah. I see your sign change, but I can't justify it using this. Anybody got 5 minutes left to try and solve this? I don't think I made a sign error. Z6 take 1. Z squared minus I minus minus plus 1 here. That divided by that, z to the 4, that times that is z6 plus z to the 4, subtract those as minus z to the 4. Minus 1 continues down. So minus z to the 4 above z squared minus z squared, yes. Times it, minus z squared again. Minus z squared is going to be plus z squared minus 1. Yeah, I can't see why that's working. Unless any of you guys can spot a mistake I made or give me justification, I will probably leave this until tomorrow and see if I can find a solution for it. Why you get those two. Yeah. Anybody back who used the quadratic formula? What did you use the quadratic formula on though? How could you justify? Oh, I guess. No. No, right. We'll leave it there, guys. I'll go through this tomorrow as a starter. But I'm just trying to work out why isn't this factorizing. I know it must, but yeah. All right, we'll leave it there. Cool. And tomorrow we'll be continuing with Argand diagrams, looking at the angle and the length. Yeah, that's what we did on the last bit, though, Becca. Is all I'm saying. We found the last solution of that, didn't we? That's how we got I and minus I. Yeah, leave it me, guys, and we'll go through this as a starter tomorrow. But cool. All right, cheers, guys, and see you then.